Thank you very much, and thanks to the organizers for inviting me. I like this format very much. I hope to give you some idea within these 10 minutes about the notion of finitistic dimension for triangulated categories. And here on the bottom, you see actually two references, right? And I want to stress in particular the second reference, which is a very recent preprint by 5 authors. Some of them were at Bielefeld when the project started. And it demonstrates actually really beautifully how that notion of finitistic dimension is useful, because they are able to generalize some sort of interesting work of Niemann and others about the existence of bounded T-structures, and the concept which they actually employ is the finitistic dimension. So in the commutative setting, finitistic dimension and Krull dimension are closely related, and there have been sort of previous work where the Krull dimension was imposed, the finiteness, but it's better sort of from the non-commutative perspective to work with the finitistic dimension. So at the same time, I should warn you that their definition is not exactly the same as the one I'm giving, but mine is, I think, very elementary and is good enough for the purpose of this talk. Yeah. So let's move on. So I want to give you now the definition of finitistic dimension, and let me recall you what has been defined before. For triangulated categories, there is this notion of thickening. If you have an object X, you look at the n thickening, and basically you take sort of cones and count sort of how many cones you take or how many extensions. And in that definition, the suspension basically comes for free. Yeah? You take all suspensions and count the number of cones or extensions. And this gives you then the thick subcategory generated by an object. And one says that X is a strong generator if for some n, the n thickening is already all of T. So this concept goes back to Boндal-Vandenberg, and Rouquet defines then the corresponding dimension. And so this is usually called the dimension of a triangulated category. And now we want to modify it. And the idea is to look more closely at the suspensions. Yeah? So the extensions are for free, but the suspensions are not. And therefore we look at what I call here the Hom width. So I fix an object X and look for another object Y, sort of how far away you can get with suspensions, and there are non-zero morphisms. Yeah, so this is the definition. And then when you fix that object X, you can look at all the objects so that the, maybe distance is smaller or equal than n. So it's like a ball which you put around the object X. And this has been, in a sense, considered before. This is, I think, all of defined an object to be homologically finite if this is always finite for every object Y, this distance, or the Hom width. So now I'm already able to give you the definition of the finitistic generator and the finitistic dimension. So an object X is a finitistic generator if X is homologically finite, as I just defined. And for example, in the category of perfect complexes of a ring, any object is homologically finite. So this is for free in this situation. So the interesting condition is this one. So you want that the Hom thickening is contained in the thickening of P of X, the P thickening, and you want that for all non-negative integers. I don't expect you to digest that right away. So you will see that it is useful, and then you can contemplate about the details. And then the finitistic dimension is basically the infimum of the amplitudes for objects which are finitistic generators. So you take a finitistic generator, and actually a finitistic generator is automatically also a generator of the category. I mean, this one can show. And the amplitude is basically given by the suspensions, so that they are non-zero morphisms. So the supremum of the suspensions, so that we have a non-zero morphism. And this is now the finitistic dimension of the triangulated category. And I want to relate this now to the finitistic dimension of a ring. So I need to recall this. Namely, we look at all modules. So A is any ring, so no restrictions, associative. And we look at all modules which have a finite projective resolution. And finite means the modules arising here, the projective modules are finitely generated, and the length is finite, so up to some n. So this is what I mean by a finite projective resolution. And then the way I define the projective, the finitistic dimension is slightly different from what usually people do, but it's basically equivalent in most cases. So it's the supremum of the projective dimensions for these modules. And now the theorem is, as you expect, that the finitistic dimension of the ring is finite if and only if the finitistic dimension of the category of perfect complexes is finite. And we can be a bit more precise. Namely, we have sort of one inequality. So the finitistic dimension of the triangulated category is always bounded by the finitistic dimension of the ring. If you want a bound in the other direction, you have to be a bit more careful. Namely, you sort of fix a finitistic generator and know there is always P and Q with these conditions. And then P plus Q gives you a bound in the other direction. And as you know, I mean, more important is really the finiteness or not. The actual value of the finitistic dimension can also vary in a derived equivalence class. If you take two derived equivalent algebras, they will not have necessarily the same finitistic dimension. So this is not unexpected that there is this kind of inequalities. Okay, so this is basically what I wanted to tell you, that this dimension is useful. And I think the whole idea is really to see what it means in other settings. I mean, outside of representation theory of algebras. And as I said before, I mean, that work of these 5 authors tell you that the finitistic dimension is an interesting invariant. Of course, we don't see that in representation theory because we believe it's always finite. So then one cannot really appreciate it. So I will end with a few remarks. So basically, if we have a finitistic, oops, what I'm doing here. Oops. Oh. No, I wanted, what happened here? Yeah, so if we have a finitistic, then all objects are homologically finite. And if we have a strong generator, then this more or less corresponds to the fact that the global dimension is finite. And that implies, of course, that the finitistic dimension is finite. And this is then here seen, a strong generator always implies that there is a finitistic generator. So the other remark I wanted to make is that this notion is not symmetric. So in general, if you have a triangulated category, there is no symmetry. And this is not unexpected because we know that for rings, we have examples where the finitistic dimension on one side is infinite, on the other side it is 0. And the finitistic dimension of a triangulated category being 0 can actually be sort of understood in terms of perfect complexes. And I guess my time is over, and I thank you for your attention.